Okay, so I'm going to talk about section 9.4, polar coordinates and polar graphs. 9.4 starts with just introducing this new way of graphing and defining functions. And then it gets into the calculus, just like we do with parametric. Today we're just working on polar and how we graph with that and some odds and ends here. And then later, once we get sort of acquainted with that, we'll talk about dealing with the calculus of polar things. Okay, so a polar point is defined by r comma theta. Now the way that works is if I give you a point in the plane, instead of calling it x comma y, wherever we are, theta as in, and we're going to use radian measure here, 0, and if you think about the unit circle, this would be like pi over 2, this would be pi, 3 pi over 2, 2 pi, and then we can go around, 4 pi, 5 pi, etc. Or if we go with a negative theta, we move in that direction. And then r will just be the radius, how far it is from what we refer to as the pole. Now the pole, one thing about the pole is, it doesn't matter what theta is, pole is just when r equals 0. And r will just be the distance in general the point is from the pole. Now, there's a lot of differences here. So in parametric was still a rectangular coordinate system, right? It was just that x and y were defined independently. Polar is a completely new thing. And one thing that's quite strange about polar is that where rectangular, there's always a unique way to describe a point. It's only one x, y, it's horizontal is the x, the vertical is the y. Polar, which we'll talk about, there's going to be an infinite number of ways to define any point using polar. And that's something we have to kind of wrap our brain around, because that impacts how these graphs get generated and why these things look very, very different than what we're used to with our rectangular graphs. Okay, so first of all, we're going to talk about a polar point, and we're going to start off by, first of all, plotting this point, and then we're going to change it to a rectangular point. So if we're plotting this point, and we're not going to do a lot of plotting polar points, we'll do a little bit of it. You should be able to do it, but especially when it comes to functions, these things can be quite involved. Once we get to polar functions, we'll be using our calculator to graph them. We're not going to spend a lot of time graphing those by hand, even less than what we do with parametric. Okay, so first of all, you find your theta, which is 5 pi over 3. So this is our r, this is our theta. Okay, so theta is 5 pi over 3, so that means that 5 pi over 3, we are over here. Okay, so 5 pi over 3 as in 5 pi over 3, right? So just like if we're talking about the unit circle. And then our point is going to be 2 away. Okay, so this, right here, let's make this dotted. Okay, so this is going to have a length of 2, and this is going to be our point 2 comma 5 pi over 3. Now, one thing I want to point out to you here is, like I said, there's an infinite of ways to graph that. One, the simplest is to just say 2 comma, and then actually we can go all the way around again. So that could be 5 pi over 3 plus 2 pi. So that'll be 6 pi over 3. So that would be 11 pi over 6. So that would be the exact same way to describe that point, 11 pi over 3. Another way to describe that point would be 2. And then instead of going positive direction, we could go negative pi over 3. Okay, so that's going to be that same point. So negative just means instead of going our normal way, we're going to go back actually clockwise as negative. Another thing is we could use a negative radius. A negative radius means you're off 180 degrees in the opposite direction. So I could do negative 2 pi over 3, and that would also give me that point. So something, it's a little different here. You got to get used to that. So just so we're clear how that works is, this over here would be theta equals 2 pi over 3, and instead of going positive r, Negative means you go back the opposite direction. Okay, so if you do see a negative r, that's what it's going to be. So the first thing we're going to do is we're going to take polar and we're going to change it to a rectangular. So multiple ways, literally an infinite number of ways to describe that point using polar, but there's only one way to describe it using rectangular. And once again, when I talk about rectangular, we're talking about typical xy. Now, it's quite easy to change polar to rectangular. We're just going to use basically SOHG-TOA, right triangle trigonometry here. So what we're going to end up getting is we're going to end up getting, so SOHG-TOA, this will be sine of theta equals opposite over r. So if I want to find y in terms of theta and r, y is going to be r times sine of theta. Now, if you're sitting here thinking, oh wait, that's kind of like unit circle, think about that. Y is sine in unit circle, but of course in the unit circle the r is 1. So this is right in line with what we've done with the unit circle. And x, of course, we can get this the same way. X is going to be r cosine of theta. So it's really quite easy to start with a polar coordinate and get to a rectangular coordinate. So these are all our polar coordinates. Our rectangular coordinate is going to be, so x is going to be r, so 2, and then cosine of 5 pi over 3, comma, okay, and then 2 sine 5 pi over 3. And now, of course, with the sine and cosine, I'm going to go to the unit circle. So using the unit circle, we have 2, 3, 4. We have right here. What's our point? Our point is 1/2 negative radical 3 over 2. So 2 times cosine. Cosine is the x, so that'll be 1/2, comma, 2 times negative radical 3 over 2. And what we end up getting is 1, comma, and negative radical 3. And that gives us our rectangular coordinate, which is unique versus the infinite number of polar ways. Okay, so pretty straightforward to go from polar to rectangular. We're going to now talk about, in our second example, how to go from rectangular to polar, which is a little bit more complicated. Okay, example 2, we're going to go from rectangular to polar. So this is rectangular, so x comma y. By the way, we're using this because we are going to get values that are special values. So for the sake of plotting, this, if we calculate it, approximate it using a decimal, is about negative 5.2-ish. Okay, so this is what we're going to use for this. And as I talked about, when it comes to rectangular, there's only one way to describe any point. So this is going to be just like always. So 1, 2, 3, 4, 5, and that's 6. And then we're going to go 1, 2, 3. So this point is closer to 5 and 6, and that is our rectangular coordinates. Okay, now how do we change rectangular to polar? So one thing I want to point out is really when it comes to this drawing, we can use any trig functions, anything that sort of matches up. So the first thing that might jump out at you, to get the r being the first thing, we're just going to use the Pythagorean theorem, right? So that's pretty common sense. So x squared plus y squared will equal r squared. R could be positive or negative. As I talked about, there's going to be a number of ways to do this. And I'll describe that point using both a positive r and a negative r. Some other things that end up coming up, first of all, you might notice that tangent of theta is equal to y over x. Okay. Now, when it comes to finding a point, usually what I do is I just find a reference angle because there's going to be a lot of different ways to do that. So to find the reference angle, so to get r, we'll just use the Pythagorean theorem, x squared plus y squared equals r squared. To get theta, since there's going to be a number of different ways I can describe using theta, there's really only 2 different r's you can use, either the positive or negative. I'm just going to go with the positive. So in other words, I'm going to do arctangent or inverse tangent, and then I'm just going to do the absolute value of y over x. And then from there, my reference angle is always going to give you the distance or the angle measurement between the ray and the x-axis. So this would be our theta sub r, or a reference angle, okay? Also, any other things that you see here can work, like anything at all that you can think up. So for instance, we did sine, we did cosine, we did tangent. You could have, and just to make this point, if it suits you, you could see cosecant theta. No, that's not cosecant. Cosecant theta, we could call that, what is that, hypotenuse over opposite. So that would be that there. So there's all sorts of different things, and we'll be using those at different times. All right, so how do we do this? All right, so the first thing I'm going to do is I'm going to find r. So that means I'm going to do x squared, so negative 3 radical 3 squared plus y squared is equal to r squared. Okay, so this will be, let's see, negative 3 squared, that's 9. 9 times 3, that's 27. Plus 9 is equal r squared. So 27 plus 9 is equal 36. 36 is equal r squared. So r could be plus or minus 6. Okay, and we'll do both. We'll show how we're going to get that. Now the theta, okay, so we're going to do arctangent or inverse tangent of y over x. So that's going to be 3 over 3 radical 3. And like I said, I'm doing the reference angle, so I'm just going to make this positive here, and then just think it through using the, the unit circle type thing. Okay, now what does that mean? The 3's cancel, so what I get is inverse tangent of 1 over radical 3. Now, just like when we did before, we know there's only so many combinations. We know this is either pi over 6 or pi over 3 because I have that radical 3 in there. So realize, in order to get 1 over radical 3, this has to be 1/2 over radical 3 over 2, so the 2's would cancel. So this is my y, and this is my x, because inverse tangent on the unit circle is y over x. So if y is 1/2, right, then I know that my reference angle here, I should do this, our reference angle here is pi over 6 when my y is 1/2. Okay, so what that means is one way to describe this point would be using the positive r, so the positive r would be 6, and the reference angle being pi over 6 means that this is going to be 5 pi over 6. So that's one way to do it. Okay, I could also do it by taking 6 and then adding another 2 pi to that. So that would be 17 pi over 6. Another way to do that is to call this a negative 6. And then, so for negative 6, we're going to be using this one. Now let's use a negative theta as well. So that would be, we could do that using the negative reference angle, which would be pi over 6. That would give us that point, because negative pi over 6 is over here, and then negative 6 would push it to that point. Or we could do negative 6, and that would be 11 pi over 6. So there's all sorts of different options to describing a point using polar. So that's how we go to rectangular polar. Like I said, pretty simple. You can always think through these things. I hesitate to sort of tell you to memorize these things because it's really easy to get all of these things just by looking at sort of SOHCAHTOA, typical right triangle trigonometry. All right, I'm going to do one more example, but let's make it really, really easy. We're going to do another one rectangular to polar, and that one is going to be very easy. Okay, one last very easy one. So negative 1, 0, that would be that point. How would I describe that using polar? So my radius is obviously 1. What's my theta? I can go with pi. That works. I can also go 1 negative pi. And like I said, there's an infinite number of ways to do this. I could do 1. Let's do negative 1 and 0. Any of those is going to give me that point right there. Okay. The next thing we're going to do is actually, I want to go through and plot some points and show you what a polar function looks like. We don't do a lot of this really, because we do rely on our calculator whenever we graph. We don't typically have to graph these without a calculator. So just something, I do think it helps to kind of see this once, because we do get all these sort of spirals and circle shapes, and I think it's important to sort of see how these things get generated. Okay, we're going to deal with a polar curve, a polar function, and get a curve. We're really doing this with BASIC. These end up being quite complicated. If you've ever seen grids that kind of look like a bullseye, that would be polar graph. Basically, they're going to have radian measure here, or angle measurement, doesn't have to be radian, and then they're going to have increments, so it'll be like circles where those marks are. So what I've marked here is 1/2 and 1, because all of our outputs for R are going to be less than or equal to 1, because it's defined by sine. You'll see all these are 1, that's 1, and so basically it's going to be all sort of contained in here. Okay. The next thing I want to talk about, a little thing that's a little weird, is typically theta is the input and R is the output, typically. Just like typically X is the input and Y is the output with rectangular. Which is weird because the way the points go, it's always R comma theta, which I always have to think about. So it's a little bit different because this is the typical output and this is the typical input. So it's actually switched of the typical rectangular, okay? So I chose some values here. We're going to calculate these, and then of course we're going to use a decimal approximation, and we're just going to eyeball this as best we can. We don't have a nice polar, like I said, it kind of looks like a bullseye, and I might show you what that looks like. The reality is we don't spend a lot of time plotting these by hand anyways. So 0 goes in here. The output will be 0. Pi over 6 goes in here, the output is 1/2. Pi over 4 goes in, that's radical 2 over 2. Pi over 3 goes in, that's radical 3 over 2. Pi over 2 goes in, that's 1. 2 pi over 3, that's back to radical 3 over 2, not negative but positive. That will be radical 2 over 2. 5 pi over 6 is back to 1/2. Pi is going to be 0. And then 7 pi over 6, that is where we're done. So the negative, that one's going to be negative 1/2. And you'll see something ends up happening here, which I'll talk about in a moment. All right, so just for the sake of graphing these, radical 2 over 2 is roughly 0.7. Radical 3 over 2 is roughly 0.87. Okay, so we're just going to do our best we can with plotting these. So we start off 0. So 0 would be this way, but we're at the pole. So the pole's always easy. Whenever R is 0, we're at the pole. Okay? So then pi over 6, and I marked these pi over 6, pi over 4. I did not measure these using a compass, so if they're a little bit off, forgive me. So pi over 6 is 1/2. So that's going to be right here. Pi over 4 is about 0.7. So let's see, closer to the half. So I'd say that's a good 0.7. Pi over 3, we're at radical 3 over 2, about 0.87, so that's actually quite close to the 1 here. And I think this should be higher up, but that's all right. We'll get a general shape. And then, of course, at pi over 2, we're at 1. Okay? And then we repeat that process again because we get these same values. So at 2 pi over 3, we're at, like I said, about 0.87. So right in here. At pi over 4, 0.7. So closer to 1/2. Then 1. And then 5 pi over 6, we're at 1/2. And then when we get to pi, which is over here, we're back to the pole. All right. Now, what happens when we go 7 pi over 6? So 7 pi over 6 is over here. Okay. Well, 7 pi over 6, our radius is negative 1/2, which means instead of going this direction, we go there. So what you're going to see as we go along, so when we're at the next point, it's going to give us this. So this just starts repeating itself once we get from pi to 2 pi. It's going to repeat itself, except instead of our all our radii being positive, they're going to be negative. So it's just going to repeat this shape. So this shape looks something like this, kind of elliptical. Okay. And that is our polar graph. Not too bad. Definitely not perfect, but that's what a polar graph looks like. And like I said, I'm going to show you how to do these on your calculator for the time being. Just sort of understanding how this gets replicated is all I need from you, not just today, but going forward. And you're gonna start seeing that we get all sorts of different shapes. We get like roses with different petals, we get spirals, there's all sorts of things that we're gonna do. Okay, we're gonna do one last thing, look at some different graphs and also changing polar to a polar equation to oh, by the way, if I wanted to change this to a Cartesian, we could. And the way I would do this, and there's a lot of different ways to do this, but I want to remind you that we have those formulas like x squared plus y squared is equal to r squared. We also know that y is equal to r sine theta. So what I can do here is I can multiply both sides by r, and usually when you're doing these you want to be a little clever. So we get r squared equals r sine of theta. And so whenever I want to change something from polar to a rectangular, we just want to replace all the r and theta stuff with x and y stuff. So r squared would just be x squared plus y squared. Definitely not something that's going to be easy for us to graph using rectangular. And then r sine of theta is just equal to y. So this is actually the equation in rectangular that will give us this. Okay, let's do one more example and then that will be it for our introduction to polar equations. Okay, the last thing we're going to do is we're working with some very basic equations here, polar equations, and I'm going to do two things. First of all, I want to graph what these are going to look like, and then I'm also going to change them to a rectangular format, and that's basically going to be it. This first one, one thing we want to think about is what the constants do. We know it's very easy with rectangular what the constants do. If I tell you x equals some value, that gives us a vertical line. If I say y equals some value, I get some horizontal line. That's not the way polar works. Okay, so r is equal to 1 here. What that means is my r is always 1. Doesn't matter what theta is. So if you get confused, think about different points. So really what this is going to give us is really just the unit circle, right? The radius is always 1. Right, so the types of points we're going to get here. Ooh, that was going so well. Just think of this as being a circle with a radius 1. So that would be like 1, 0. Actually, like I said, it does end up being a unit circle. Okay, so how am I going to change that to a polar thing? Or excuse me, rectangular thing. It is already a polar thing. So like I said, r is always 1 here. It doesn't matter what the theta is. Theta equals 0, theta equals pi over 2, theta equals 3 pi over 2, it's always, or 3 pi over 4, it's always 1. So how do we get this? Well, the easiest thing to do here is, and I want to remind you, we have some formulas like x squared plus y squared is equal to 1, or excuse me, r squared. We have x equals r cosine theta. We have y equals r sine of theta. We also have y over x is equal tangent theta. And then actually any, if I'm looking at that circle, any trig functions I can get from this being y, x, and then this being theta and r. Right, so anything I can think of that comes from that. Okay, so what I'm going to do here is I want to use this one. So I'm going to square both sides. So that's going to be r squared. 1 squared is just 1. And then r squared, I'm going to replace it with this. So it's x squared plus y squared equals 1, which is, of course, our equation for a circle with radius 1 centered at 0, 0. All right, so that's our first, that's if r is equal to some constant. We always get a circle. Which if you think about it makes sense for polar. Rectangular, we always get rectangles when y equals. For this one, theta equals pi over 6 means theta is always equal pi over 6. So it doesn't matter what r is. This would be theta equals pi over 6. It's going to be on this line. But then also keep in mind, r could be negative. So it could go in this direction as well. And so this would be r theta equals. So wherever I have theta equals, if it was theta 3 pi over 4, it would look like this. Now, how am I going to change this? What I'm going to end up doing is I'm going to end up using, so the thing we want to realize here is this is just always going to be a line. So it's going to be y equals, and that is going to be the slope of that, which is going to be tangent of pi over 6, and then x. So tangent of pi over 6, because that's going to be our rise or run, right? Y over x. So tangent of pi over 6 is going to end up giving us, let's see, 1/2 over radical 3 over 2. So that is y equals 1 over radical 3x, and that is our rectangular coordinates for that. Okay, r equals cosecant theta. This one's going to be very difficult to see because we'd have to like plot points until I realize what the rectangular thing is. So these were quite easy, I could think through. So how am I going to get the rectangular? Really the easiest thing to do here is multiply both sides by sine. So I'm going to multiply the left by sine, I'll get r sine of theta. Why would I want to do that? Because now I'm going to be able to use these here. And then cosecant theta times sine of theta, those of course are reciprocals. So we get 1 is equal to r sine of theta. And so r sine of theta is of course y, so I get y equals 1. So this gives us our horizontal line. So y equals 1, and this would be that equation. If we plotted this, you would end up seeing that as we go 0, etc., this will go farther out. Once you get to the other side of pi over 2, or once you get past pi, you're going to end up generating all the negatives, but this gives us y equals 1. Okay, so that is our lesson here for polar. As I talked about, we haven't done the calculus yet. Later in the week, we'll start talking about our typical dy over dx, etc. Okay, so that's 9.4.